27% of everything that exists in the universe is completely invisible. It doesn't glow. It doesn't reflect light. It doesn't interact with anything we can detect directly. We have never seen it, never touched it, never measured it in a laboratory. And yet, without it, you would not exist. The galaxies would fly apart. The stars would never have formed. The universe as we know it would be utterly different. Scientists call it dark matter, and it is the greatest mystery in modern physics. Welcome to Space Secret Explained. Today, we're going to tell you the full story, what dark matter is, how we know it exists, what it might be made of, and why some of the world's greatest scientists have spent decades searching for something they have never been able to find. The universe doesn't add up. Here is a fact that should stop you in your tracks. Everything you have ever seen, every star, every planet, every galaxy, every atom in your body, makes up just 5% of the universe. 5%. The rest is dark matter and dark energy, two completely different mysteries that will save dark energy for another episode. Today is all about dark matter. So how did we figure out that something invisible was out there? It started with a problem that physicists kept running into. The universe simply didn't behave the way it should. The spinning galaxy problem. Think about our solar system. The planets closer to the sun orbit faster. Mercury zips around in 88 days. Neptune takes 165 years. This makes perfect sense. The closer you are to a massive object, the faster gravity pulls you around it. Now apply that logic to a galaxy. If all the mass is concentrated at the bright, glowing center, which is what we can see, then the stars at the outer edges should orbit slowly, just like Neptune crawls around the sun. But when astronomers actually measured the orbital speeds of stars in galaxies, they found something that broke the model completely. The stars at the outer edges were orbiting just as fast as the stars near the center. In some galaxies, even faster. This is called the flat rotation curve problem, and it should not be possible unless there is a massive amount of invisible matter spread throughout and around the galaxy, providing extra gravitational pull that we can't see. Matter that isn't glowing. Matter that isn't there in any form we recognize. Vera Rubin and the smoking gun. The person who made this undeniable was an astronomer named Vera Rubin, and her story is one of the most important and most overlooked in the history of science. In the 1960s and 70s, Rubin began systematically measuring the rotation speeds of galaxies. She was meticulous, careful, and thorough, working through galaxy after galaxy after galaxy. And every single one showed the same thing. The stars at the outer edges were moving far too fast. Every galaxy she looked at was rotating as if it contained far more mass than could be accounted for by the visible stars and gas. The physics was clear. Either gravity doesn't work the way we think it does at galactic scales, or there is a vast amount of invisible matter wrapped around every galaxy, holding it together like a giant cosmic cocoon. We became astronomers thinking we were studying the universe. We now know we were just studying the small fraction of it that glows. Vera Rubin. Vera Rubin never won the Nobel Prize, a decision that remains controversial to this day. She died in 2016, but the evidence she compiled, combined with independent lines of evidence from gravitational lensing and cosmic structure, has made dark matter one of the best supported ideas in modern cosmology. The bullet cluster. If you want the single most powerful piece of evidence that dark matter is real, it's the bullet cluster. About 3.7 billion light-years away, two massive galaxy clusters collided, one of the most violent events in the observable universe. And what happened when they hit gave us something remarkable. When two galaxy clusters collide, the ordinary matter, the hot gas that makes up most of a cluster's visible mass, slows down. It clumps together in the middle, slowed by electromagnetic interactions. You can see it glowing in X-rays, but astronomers also mapped where the gravitational mass was. by measuring how the cluster bent the light of background galaxies behind it, a phenomenon called gravitational lensing. And the mass was not in the middle with the gas. It had sailed straight through the collision, barely interacting at all. The two clusters' mass had passed through each other like ghosts. This is the smoking gun. Ordinary matter was slowed by the collision. The invisible matter, dark matter, wasn't. It doesn't interact electromagnetically. It barely interacts with anything. It just passed straight through. This is the closest we have ever come to directly seeing dark matter, by watching what it does rather than what it is. What dark matter might actually be. So we know dark matter exists. We know roughly how much of it there is. We know where it tends to gather. But we have absolutely no idea what it's made of. This is the question that has driven particle physicists, cosmologists, and astrophysicists to a kind of collective obsession for 50 years. Let's go through the leading candidates. Candidate 1. WIMPs, weakly interacting massive particles. For decades, the most popular theory was WIMPs, weakly interacting massive particles. The idea was elegant. Dark matter might be a heavy particle, perhaps 10 to 100 times the mass of a proton, that only interacts through gravity and the weak nuclear force. WIMPs were theoretically beautiful because they arose naturally from supersymmetry, an extension of the standard model of particle physics that many physicists considered almost inevitable. If supersymmetry was right, WIMPs should exist. The problem? Decades of incredibly sensitive experiments have failed to detect a single WIMP. Underground detectors, particle accelerators, space telescopes, nothing. If WIMPs exist, they are hiding extremely well. Candidate 2. Actions. A different candidate, and one gaining significant attention, is the axion. Actions are hypothetical particles that are incredibly light, perhaps a trillion times lighter than an electron. They were originally proposed to solve a completely unrelated problem in physics, but theorists quickly realized they have exactly the right properties to be dark matter. Experiments like ADMX in the United States are right now scanning specific frequencies looking for the faint signal actions would produce when exposed to a strong magnetic field. Candidate 3. Primordial black holes. A third, wilder possibility. Dark matter might not be a particle at all. It could be tiny black holes, called primordial black holes, formed in the first fractions of a second after the Big Bang, before any stars existed. These would be incredibly small. Some theories suggest they could be the mass of an asteroid compressed to a microscopic size. They would interact gravitationally, but barely at all any other way. Stephen Hawking explored this idea. Even Elon Musk has referenced it. It remains a live hypothesis. Candidate 4. Something we haven't thought of yet. And then there is the humbling possibility that dark matter is made of something physics hasn't predicted at all. A particle outside our current models entirely. Something waiting to be discovered that will require a completely new chapter of physics to understand. How we're trying to find it. The search for dark matter is one of the most ambitious scientific hunts in history. Scientists are coming at it from 3 directions simultaneously. Direct detection, underground laboratories, deep underground, in abandoned mines in South Dakota, in tunnels beneath the Italian Alps. Physicists have built tanks filled with ultra-pure liquids, shielded from every known source of radiation. The goal? Catch a dark matter particle if it occasionally bumps into an ordinary atom. These detectors must be underground because cosmic rays would otherwise drown out any signal. They must be extraordinarily pure because even a single atom of contamination could fake a detection. The LUX Zeppelin experiment in the Sanford Underground Research Facility is currently the world's most sensitive. So far, nothing. But the search goes on. Production at colliders. At the Large Hadron Collider at CERN in Switzerland, physicists smash protons together at nearly the speed of light, hoping to produce dark matter particles in the wreckage. If dark matter particles were created, they'd escape the detector invisibly, leaving a signature of missing energy that physicists could measure. So far, the LHC has not found any sign of dark matter. This has actually ruled out a huge range of WIMP models, which is itself scientifically valuable, even if deeply frustrating. Indirect detection from space. If dark matter particles can occasionally collide and annihilate each other, they should produce gamma rays or other radiation. Space telescopes like NASA's Fermi Gamma Ray Space Telescope scan the universe looking for unexplained bursts of gamma radiation, particularly from the galactic center and from dwarf galaxies, where dark matter is thought to be densely packed. There have been tantalizing hints over the years. An excess of gamma rays from the galactic center that no known source explains, but nothing conclusive yet. Could we be completely wrong? Science demands that we ask the uncomfortable question. What if dark matter doesn't exist? What if we're wrong about gravity instead? There is a minority but serious scientific position called MOND, Modified Newtonian Dynamics, which proposes that our equations for gravity need to be tweaked at low accelerations, like those experienced by stars at the outer edges of galaxies. MOND actually works remarkably well at explaining galaxy rotation curves without dark matter. Its founder, physicist Mordechai Milgren, proposed it in 1983, and it has never been fully discredited. But, and this is a large, but MOND struggles badly with the bullet cluster. It cannot easily explain how the mass of two colliding clusters separated from the gas. And it fails to explain the large-scale structure of the universe, the pattern of galaxies and cosmic web that dark matter models predict almost perfectly. Most physicists believe dark matter is real, but the failure to directly detect it after decades of searching has kept alternative ideas alive. Science works best when it keeps questioning what finding it would mean. Let's imagine we find it. A physicist looks at data from an underground detector, or from CERN, or from a space telescope, and there it is. An undeniable signal. A particle that fits. The discovery of the century. What changes? Everything. Dark matter is the scaffold of the universe. It formed first after the Big Bang, and ordinary matter fell into the gravitational wells it created. That's why galaxies formed where they did. Understanding dark matter means understanding the origin and structure of everything. And practically, we would have discovered a new particle, a new force, potentially a new sector of physics entirely invisible to us until that moment. The technological implications are impossible to predict. Discovering electromagnetism led to electricity. Discovering the nucleus led to nuclear power. Discovering dark matter could open a door we can't even imagine yet. Dark matter is not just a cosmological curiosity. It is a window into physics beyond everything we currently know. Catherine Fries, theoretical physicist. We live inside a universe we cannot fully see. The matter that built you, that powers the stars, that makes up every telescope and detector we've ever built, is less than 5% of what's out there. The rest, most of reality, is dark, silent, unknown, but not undetectable, not forever. Every year, our detectors become more sensitive. Every year, our telescopes see further. Every year, physicists think of new approaches that weren't possible before. The answer is coming. We just don't know when. If this video made you see the universe a little differently, that's what Space Secret Explained is here for. Subscribe so you don't miss what's next. Because in the next episode, we're going somewhere even darker. We're asking what the universe looked like before the Big Bang, before time itself began. Until then, keep looking up. And remember, most of what's out there is still waiting to be found.